Spectroscopy can be difficult to understand because it can be done a ton of different ways. However, all of them have to do with the material and its absorption of radiative energy. Spectroscopic study can be divided into three different categories. These are the type of radiative energy being studied, the interaction between the energy and the material, and finally the material itself. The first category, the type of radiative energy, can be divided into four different subcategories. The first being the study of electromagnetic radiation. The second being the study of particulate radiative energy, that being the energy of a piece of matter that has movement and therefore has kinetic energy. Third, acoustic spectroscopy can be studied by measuring pressure via sound waves. And lastly, mechanical spectroscopy, while similar conceptually to acoustic, studies pressure waves that are able to travel through solid materials. The second category of spectroscopic study is a type of interaction the radiative energy has with the material it's being observed on. The first subcategory here is coherent spectroscopy. This has to do with high radiation energy that is able to bond two different quantum states in a material, typically used to study nuclear magnetic resonance. The second type of interaction is absorption. This is when the energy transmitted through material is less than it was before it passed through. How the material absorbs the energy is cross-referenced with existing data to draw similar connections. The third type, emissions, is where the energy is being radiated from a material such as flames or sparks. The fourth category is inelastic scattering. This is the study of how a material scatters high energy waves that pass through it. The last type of interaction is impedance spectroscopy. This is the study of how a material slows down the transfer of energy passing through it. The last category of spectroscopic study is categorized by the material being affected by the radiative energy. These materials can be broken down into four different types. The first category is the study of energy on the atom. This is observed through analyzing the atomic spectral lines. The second material is the molecule. The combination of different atomic spectral lines can often give a bigger picture and shed light on rotation and microwave spectroscopy. The third is crystal spectroscopy. This not only studies the combination of spectral lines from the atomic level, but can be used to study mechanical radiative energy as well. The final material studied in spectroscopy is a nucleus. Because nuclei have distinct energy states divided into magnetic fields, the emission of light waves from said fields are able to be studied.
Usually, spectroscopy is thought of as the classical glass prism with white light shining into it and a rainbow shining out of it, or the colorful absorption lines. These are usually a result of ultraviolet visible spectroscopy. However, this is only a fraction of the entire electromagnetic spectrum, and will not provide a complete picture as to what goes on in our universe. Infrared spectroscopy offers to uncover just as many mysteries as ultraviolet visible, if not more. A joint project between NASA and the German Aerospace Center has been implemented since 2010 to aid scientists research and understand the universe in the infrared spectrum. This project is called SOFIA, the Stratospheric Observatory for Infrared Astronomy. Its name literally implies that it is an observatory for infrared astronomy that is directly in the stratosphere. How is this even possible? Well, I'll tell you how. SOFIA is a Boeing 747 SP with a garage door sized hatch on its side. So all of the onboard telescopes and instruments have an unobstructed view to the sky. What you might be asking is, why is it necessary to use a plane to study infrared spectroscopy? This is mainly due to the large amounts of water vapor between the ground and the edges of the atmosphere. Therefore, rising as high as possible would significantly reduce the amount of water vapor blocking the view of the telescopes and instruments. Something you may ask is, why is infrared spectroscopy important? To answer, infrared spectroscopy helps astronomers observe molecular vibrations. Observing molecular vibrations then helps identify functional groups, which are groups of atoms that give a molecule certain characteristics and properties. Studying the vibrations of molecules and their activities can provide useful information about black holes and star formation. SOFIA has several tools to perform infrared spectroscopy, such as FlightCam, a near-infrared camera, XS, a high-resolution infrared spectrometer, Forecast, a mid-infrared camera, and Hawk Plus, a far-infrared camera and perimeter. Focusing on infrared spectroscopy on SOFIA has allowed for numerous discoveries, such as mapping of the dwarf planet Ceres, Jupiter's circulation patterns, atomic oxygen on Mars, and terahertz water masers, just to name a few. Who knows how far infrared spectroscopy will lead us in understanding the universe in the near future. If you are at all interested in infrared spectroscopy or SOFIA, then you may hold the keys that can unlock future discoveries in this field.
SOFIA? Oh, no. Not SOFIA, the robot that's trying to kill us all. SOFIA, as in the Stratospheric Observatory for Infrared Astronomy. It is the largest airborne observatory in the world, capable of making observations that are impossible for even the largest and highest ground telescopes. Studying the universe using only visible light results in a very limited view, as you can see from basically this and this. Visible light, the light you see with your eyes, reveals only part of the universe. Astronomers observe many other types of light to expand our views of the universe. And it just so happens our handy dandy best friend, SOFIA, is able to observe the infrared universe. Many objects in space emit almost all their energy in infrared wavelengths. OMG. This means basically almost everything is invisible when observed in ordinary visible light. But that's definitely not going to stop us because we have SOFIA. So, you might be asking, like, what exactly or how exactly does SOFIA work? Don't fret. Listen to this. So, basically, SOFIA uses these instruments. No, not those instruments. She uses cameras, spectrometers, and photometers. They operate in near and mid and far infrared wavelengths, some better than others, but that's beside the point. Alright, so SOFIA has two instruments: the First Light Infrared Test Camera, called Flight Cam, and the Faint Object Infrared Camera for the SOFIA telescope, Forecast. These instruments have grisms covering the entire 1 to 40 microspectral region required for studying dust grain mineralogy and IR forbidden line emission with the required spectral resolution, of course. But that's not all. SOFIA can fly anywhere and anytime to enable observations of targets of opportunity and can observe objects as close as 20 degrees to the sun. 20 degree to the sun. That's real close. But can SOFIA really put her money where her mouth is? Duh. The first CN to be observed with SOFIA showed a high, rich hydrogen recombination line spectrum associated with free development phase. Basically, that means SOFIA is crisp AF. SOFIA has the unique potential for greatly expanding our understanding of the IR temporal development of CN. At least one of these SOFIAs isn't trying to kill us all. As you can see, SOFIA's technology enables us to see beyond our wildest dreams and learn even more about star births, deaths, and everything in between. So come along with us. Continue to learn and explore the deep depths of our universe with us. For more information about spectroscopy and SOFIA, visit nasa.gov.